Hello students, welcome to the next video in magnetic fields. This time we're going to look very quickly, hopefully, at the solar wind. What is the solar wind? Well, the solar wind comes from our sun and it consists of charged particles being electrons or protons that are coming from the sun. They're ejected from the sun and they go out in all directions from the sun, but some of them hit the earth. They cause auroras, communications interference, and what's called space weather. You wouldn't think there's weather in space because space is full of nothing, but there is this thing called space weather. And there's a link here to a web page which I'll put on the OneNote where you can look a lot more into the solar wind if you wish. Now this is a picture of the sun, just showing you that particles are being emitted in all directions, and they have different velocities depending on some of the directions that they come out, and you can have things called flares which, although they emit particles, charged particles, protons and electrons that are slower than the general population, these being fastest, that's the speed there, you get a more massive amount, and things like solar flares are very directed emissions of particles, and that's one of the reasons why we have satellites up there watching the sun to see which directions these solar flares are emitted and if they're ever emitted in our direction. So this is the variation. The sun, you might think, is just this glowing orb in the sky. And it's pretty consistent, but in terms of its physics and what's actually happening on the sun, it's a very dynamic body, and it's varying, and this is the variation in a whole lot of parameters which you don't need to know about too much, but just shows that the sun is varying and people are very much interested in watching the variation in the sun on a day-to-day basis. So you should be able to do question 10 now. Now the sun has a magnetic field, and it's a very complicated magnetic field, much more complicated than the Earth's, and these are two representations of the sun's magnetic field. It's much more complicated because the sun doesn't just have a north and a south pole, it actually has all sorts of poles popping up everywhere. It's much more convoluted, asymmetrical is probably a good word, magnetic field, because it's such a dynamic swirling mass of plasma, and it varies, and this is some modeling showing that with the variation. So just as the Earth's magnetic field undergoes reversals, and we'll talk about that I think in the next video, the sun's magnetic field undergoes reversals pretty much all the time on a regular basis, and so it can become very stable like this, or very regular, with a north and a south and the magnetic field lines forming nice big loops, but then it can break down and have this chaotic magnetic field where there's lots of norths and souths all over the place popping out of the surface, and this is during a reversal, which may hint at what might happen if the Earth's magnetic field undergoes a reversal. Some things where those poles are popping out of the surface are represented by these black areas, sometimes also referred to as sunspots, and they're areas that are actually now, are they super hot or super cold relative to the rest? I think they're super hot relative to the rest of the surface, and it's where magnetic flux lines are coming out of the surface, and this is a time lapse showing the variation in those sunspot activity. And some people use sunspots or the regularity of sunspots for all sorts of things, and some people actually postulate that sunspot activity has had a major role in the Earth's climate. So here's a picture of the sun, and you can see the field lines going in and out, and so wherever they come out is a south and wherever they go in is a north, and so they have these loops and the field lines go here, and what happens is that plasma ejected from the surface of the sun follows these magnetic field lines, and that's why you can see them in these sorts of things. And there's a really good video showing this, which will be on OneNote, sunspots.mpeg. I'll see if I can get some more actually, I'll put them on the OneNote. Now, we've been studying the sun for a while, but our imagery of the sun has gotten better and better, and right now we're using a thing called SDO to give us the best high resolution images of the sun that we've seen. And these were pretty much put out last year, I think. And this is what the sun now looks like, and you can even go onto the web and get high resolution images of this. And so it's swirling masses and solar flares coming off all over the place. Very active and dynamic place. And some more images of the sun, quite spectacular. Well worth having a look, and you'll see some on the video as well. And there's a solar flare. So this is the surface, swirling mass of plasma, and these solar flares erupt off the surface, and some of this material will be ejected into the into space in that direction. And when one of those is actually pointing at Earth and happens, alarm bells go off, because people have to be aware of a sudden stream of charged particles. And just to give you a scale, sometimes it's hard to realise how big the Earth is. That would be the approximate size of Earth relative to the Sun. And there's one of these protuberances, the solar flares sending off. So if Earth was there, it would get swallowed up pretty easily. So a couple of videos here. This one's the sun performs for SDO, and this one, new solar images. They'll be on the OneNote. And so not drawn to scale, but this is what's happening. So a flare happens here, charged particles come out, and remember the Earth's magnetic field, it's distorted because of this solar wind, and the charged particles get funneled, and we'll show you that. There's a couple of videos that show this. In terms of what's happening to the sun and sunspots MPEG. Right. We'll go back to that diagram quick, but as a result, let's just quickly go back. As a result of these charged particles coming in here, we get what's called auroras. And if you haven't seen auroras, some Tasmanians are lucky enough to see them, but we really don't get to see them as well as other countries, especially in the northern hemisphere. Auroras are bright lights in the sky. This is the northern lights, and these are the southern lights. So this is down in Antarctica, and you get these sheets of light that move across the sky. Again, northern lights, and these would be flickering. And this is the interaction of charged particles with the upper atmosphere, and the charged particles come from the solar wind. And you get these green. Often photographs can't do these enough, and so I've got a couple of videos for you to see as well. And these are nice. Green is a common colour, again in Antarctica this case, and grey bluey green in Antarctica. And so what are they? Well, they're caused by the collision of the charged particles with the Earth's magnetosphere and the atoms in the upper atmosphere. So in the upper atmosphere, atoms are being bombarded effectively by these fast-moving electrons. They cause the atoms to get excited because these electrons and protons have a fair amount of energy, and they get them excited, and then when the atoms lose their energy, they emit the energy in the form of light, and that's what we're seeing, the auroras. And we'll be doing this, looking at this sort of activity a bit more in atomic physics. So there's a video there which is called Auroras. There's one called Dancing Auroras, which is in HD, which is good. And then there's one Auroras, Northern Nights, Canada, one night. And they'll be on the OneNote. Not very long. Have a look at them. Pretty spectacular. And if you ever get the chance to go somewhere where you could see auroras, I know a lot of tourists that go to Europe head up into Finland and Sweden just to go and look at auroras. There's a whole tourist industry related to it, and they are quite spectacular. And so this was the diagram I was mumbling about before, which I thought was earlier, which is here, the sun's out here, charged particles come in and they interact with the Earth's magnetic field, and they get funneled basically towards the poles. And then you have these plasma belts, which are the Van Allen belts, but we're mainly interested in these interactions here, which cause the auroras. And so this is what they look like from space. So the charged particles are coming down the magnetic field and then start to interact with the atoms here in this. And this is probably a truer colour representation of what they look like. And again, there's Antarctica, there's Tasmania, and we might just be able to see some of these occasionally. There was actually an article in the Mercury the other day saying be on the lookout for auroras in Tasmania. You might see them if you're lucky. What have we got here? Volcanoes, and there's an aurora. So this is in the Northern Lights. That's a combination of two fantastic things. How good is that? And there's the auroras again, and volcanoes, and there'd be lightning and stuff. Fantastic. And there's the aurora again. Isn't that spectacular? So this is the solar wind and the interaction that Earth has with the solar wind. And it can make pretty lights, but it can also be bad. Why? Because the electrons can damage spacecraft and electronics. So they can knock out satellites. They can interrupt GPS, which is used virtually for most transport things nowadays. Can affect the plane's avionics, cause disturbance to radio signals, cause huge currents in power lines because they can induce currents. And when we do electromagnetic induction, we'll work out how that happens. And in submarine cables, they can cause surges. And so there's actually a recorded case of a major blackout in either Canada or America a couple of years ago, which was caused by a huge power surge caused by a solar flare activity, and it knocked out all the substations and caused the blackout. So now people are aware of them, more aware of them, and have to be a bit more careful and plan for them. Interestingly, they can also cause currents in pipelines. And so something that you wouldn't think is related to electricity is, say, an oil pipeline or a gas pipeline. But when the solar wind activity or flare activity happens, you generate this big current. And if you haven't got a system in place to get rid of this current, it can completely destroy things. So a lot of time and effort and money is spent in preparing for such cases. Now there is, of course, the whole solar wind sending neutrinos towards the Earth and causing the inside of the Earth to boil. That sounds pretty dramatic, and it has been seen in the movie 2012, which was, of course, science fiction. The solar wind does not cause the inside of the Earth to boil, but it made for a good movie with lots of disasters. So in the next video we'll look at actually geomagnetism. Cheerio!